the last episode for the first chapter of Ethiopian Artificial Intelligence Center AI seminar. So on today's episode, we have Professor Yoshua Bengio from Mila, Montreal, Canada. Yoshua Bengio is recognized as one of the world's leading experts in artificial intelligence and pioneer in deep learning. Since 1993, he has been a professor in the Department of Computer Science and Operational Research at the Université de Montréal. CIFAR's Learning in Machine and Brains program co-director. He's also the founder and scientific director of Mila, the Quebec Artificial Intelligence Institute, the world's largest university-based research group in deep learning. In 2018, Yoshua Bengio ranked as the computer scientist with the most new citations worldwide, thanks to his many high-impact contributions. In 2019, he received the ACM A.M. Turing Award, which is the Nobel Prize of Computing, jointly with Geoffrey, Hinton, and Yann, LeCun, for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. This honors reflects the profound influence of his work on the evolution of our society, concerned about social impacts of this new technology. He actively contributed to the development of the Montreal Declaration for Responsible Development of Artificial Intelligence. Thank you so much, Professor Yoshua, for your willingness to talk about AI advances, challenging societal opportunities, even though you're the busiest person I know. Thank you for accepting our invitation with a search notice.
My pleasure. Thank you, Israel. It's a pleasure to be sharing my thoughts with every one of you. Let me get started. So get rid of this. So I will start with how I got into this field when I was a grad student. I got very excited reading some early neural network papers. And what really made me enthusiastic is the idea that there might exist a few principles, just like the laws of physics, that could explain intelligence, both our intelligence and animal intelligence, and of course allow us to build intelligent machines. So that's something that I still believe in and is driving a lot of my research. Now, for this dream to be concrete, what it means is that instead of intelligence coming out of a big bag of pieces of knowledge, it's driven by a simpler program, if you want, a simpler set of meta knowledge, which is machine learning. Which is learning how to learn, right? So now instead of having to describe all of the knowledge in the world when we want to build an intelligent machine, it's enough to just tell the machine how it can figure out those things from experience, from data, from interacting with this environment. So that's one difference with the classical AI approach that existed when I started my grad studies in the 80s. That knowledge is not just provided by humans, but it's provided by experience. There are also reasons why it was tempting to move toward machine learning. There are some issues with classical AI based on rules and so on. Like they're not really good at handling uncertainty. They're not grounded in low-level perception and action. And these issues have been dealt with in large part with machine learning and especially modern machine learning, but there's still, we're still at the beginning of this journey. And in particular, although we've made a lot of progress in low-level perception and to some extent, low-level actions, we haven't really been able to build machines that can discover by themselves the kind of high-level abstract representations and cognition that humans enjoy, which allow us to do pretty amazing things. And I'll talk more about it at the end of my presentation. So another particularity, that really attracted me, the idea that these principles would be shared between machines and humans and animals And so that really suggests that in AI research, we could get inspiration for potential principles and algorithms from looking at animal and human intelligence. So inspired by the brain, essentially. And what we see when we look in the brain is a large number, like 88 billion in your brain, about of small adaptive computational units, which are the neurons. And that is, that's the idea that gave rise to the whole field of neural networks. Now, something that came in the 80s that I also caught on and has been at the heart of much of my research for decades is the idea of distributed representation. So that information is represented as a pattern of activations rather than by symbols. And that gives rise to powers of generalization that I'll come back to later. In particular, I worked on word representations, word embeddings in around 2000, and it has really changed the field of natural language processing. Now, in order to try to structure our thoughts about how learning in general can work, whether in brains or in machines, it's nice to kind of divide the problem into pieces. And in machine learning, the common way of thinking about this is that intelligence arises from the combination of three things: an objective function or reward function that you're trying to optimize, a mechanism for optimizing it, an optimizer, which is going to be imperfect and approximate, like a learning rule, and the class of functions or the architecture, how you parameterize the set of functions you could learn. So that's like the structure of a neural net. And with this, we can learn, all of the pieces, all the parts of the system together with respect to one objective function. In reality, in modern machine learning, people are exploring more complex variations on that theme, but it's a very important theme that has been extremely successful in deep learning. Now, another reason why I got excited about neural nets, and this really became important for me in the 90s and 2000s, is understanding the limitations of other machine learning methods that were not based on neural nets, like kernel machines and other non-parametric approaches in statistics. And the issue is sometimes called curse of dimensionality. Simple-minded approaches, a lot of simple-minded approaches in machine learning have been proposed, where really it amounts to learning from examples locally. So in one dimension, if I take let's say I have a single variable of interest and I discretize it into bins, and I just observe how many times do I see an event in each of the bins, and with that I can answer in the future by the frequency of this happening. And if I have to predict a variable, I would have for each bin in X, I would store the average values of Y's, for example, in each bin. So that's a simple. I mean, you can do slightly better with kernels and make it smooth, but the problem is when you go to high dimensions with these kinds of non-parametric methods, most of the bins, most of the cells in high dimensions will be empty. There's no data there. There's just a number of possible configurations of variables is too large that there's no chance that we can cover the whole space. This is something a lot of people forget. And this is something that neural net approaches are more generally approaches that bring in more structure, more inductive biases, more assumptions about the world, allow us to bypass some of these issues. But it remains the challenge number one for generalization. How do you generalize away from the data, far from the examples? And one of the ideas that has been at the heart of understanding why neural nets are doing so good, but also at the heart of my current work to go beyond current neural nets, is the idea that you can get generalization, a powerful form of generalization, by various approaches that rely on some form of compositionality. So what is compositionality? It means that we combine different pieces of knowledge. We combine different layers one on top of the other. We combine different features in the pattern of activation. And you can do math around these things and show that you can get an exponential gain with respect to how efficiently you can represent a function, for example. And I've done a lot of work in that sense in the 2000s. Now, this is an inductive bias. It's making assumptions about the world, that we can explain the world by composing little pieces, composing concepts, composing functions like we do in programming. And humans seem to exploit that sort of thing a lot. Now, let me go back to why distributed representation can be exponentially more efficient than classical non-parametric methods like clustering or kernel methods. So on the left, you have sort of the classical ways of thinking about how to learn a function using only local information like clustering, for example, or k-nearest neighbors. So what you see on the left is, say the input space is two-dimensional. And what we'd like is to learn a function that for each input provides an answer, input X provides an answer Y. And what we could do is where we have data, we could say, well, in some region around these data points, we're going to produce an answer based on the examples we have for that region. So we partition the space into regions, and in each region we see what kind of data we have. So it's like the same thing I had in this slide when I said we could solve the problem by looking at what happens in each bin. Here we just generalize it to a region, and we could define the region by many different ways. Like in the picture here, maybe you have cluster centers, and you just look at what kind of answers you get in each region independently. The problem with that is, I mean, it works really well in 1D or 2D or even 3D. But if you go to higher dimensions, the number of regions you need to kind of cover the space, just because of the curse of dimensionality I just discussed, goes exponentially high, and you don't have enough data to cover new regions that are far from those you've seen. Now, compare that with distributed representations approaches, which you find in neural nets on the right. Okay, so what is being illustrated here? So we have the same input space, but the way we're going to create regions is different. We're going to create regions in a compositional way. So the way we're going to define a region is that here it's the intersection of three half planes. So how do you do that? So if you have a hidden layer with 3 units, and each unit is just like a linear classifier. So it's, you know, it's like this black curve or the blue curve or the red curve. So say the black line splits the input space in 2 halves, and the red hyperplane splits the input space in 2 halves, and so on. So now if I take the intersection of these half planes, I get actually a pretty large number of regions. And how many examples do I need to train this? Well, I need a number of examples proportional to the number of these units, these half planes, these linear classifiers. That's much less than the number of regions which I can generate. The number of regions I can generate is now exponential in the number of parameters. So this is how you win really with distributed representation, that the input is represented by a pattern of activation, like which half plane you're on one side or the other side. In this case, it's just a bit pattern, but in general, it could be how far you are from the plane. And so what's interesting, really, why you get good generalization from this is that in a way you can learn about each of these features. So these half planes, they're like features, right? And then I looked at a really simple example where I had only 3 features and each was just a linear classifier, but you can imagine more complex features. So in a convolutional net, you've got an input image, and the top hidden layer represents a bunch of features. So each unit at the top layer represents a feature. And we could try to imagine, like a thought experiment, what those features could be and why this could be really allowing us to generalize in a powerful way. So for example, you could imagine that one feature the model discovers by itself, let's be optimistic, that one feature detects that a person wears glasses or not. Another feature detects that the person is a male or a female. Another feature detects that the person is a child or adult, right? So just to make it easy, I made those features binary, but now you can see that for a particular image, you're going to have a different pattern of activation. It's like our classifiers of before. And now I can generalize to a configuration of those features, like a binary vector, basically, that I've never seen. Maybe I've seen people wearing glasses and people not wearing glasses, and so I can train my glass detector. I've seen people that are females and people that are males, and so I can train that one. And I've seen people that are children and adults, so I can train that one. But maybe I've never seen a child woman wearing glasses, and so how can I generalize to this? But because I've decomposed the problem into these features that I can learn separately, and that's essentially how neural nets are able to generalize to configurations of the inputs that they have never seen, because they learn these intermediate representations, these intermediate features. And this is not just a theory, it was kind of confirmed by trying to look at those hidden units. What are they doing? So there are a bunch of papers, for example, the work of Toral's lab, where they try to give an interpretation to the features that were learned. And they find indeed that some features will specialize in things like people or lighting or tables or animals or seating, even though they were never trained explicitly to do that. It's just that it turns out that those features are useful for the task. So to summarize, what's particular about neural nets and deep learning especially is the notion of internal representation. You don't have a notion of learned representation in SVMs or kernel machines or decision trees and things like that. What is really unique and crucial to the success of deep learning is this idea of learning representation. And that begs the question, what is a good representation? What is it that makes a representation good? And I don't think we have completely answered that, but of course we have methods to train those representations. And the main method is, well, we want the representation to be such that it's a good input for learning a difficult task, like some classification task or a bunch of other tasks. Ideally, it's something generic that applies to many tasks, as I will explain. So this is how we got into learning features. That's basically the early neural nets of the 80s. But later in 2000s, we moved to the idea that we could have features on features on features, like deep nets basically are the idea that we can compose feature extraction that are learned at multiple levels in the hierarchy. And so we can learn more complex features. And we can also show that this allows us to learn even more powerful features that can generalize even better out of distribution. So like in this example, we wouldn't be able to have a glasses detector using only a linear classifier. You need a pretty deep network in order to do that, and it needs to have the right kind of structure. So you need a deep net. And so this idea that we're going to compose computation across multiple levels in the hierarchy is something that we find in science and engineering. And it makes a lot of sense, for example, if you're trying to extract information from images, that you're going to have these low-level features like edges, and then mid-level features that combine the edges, and high-level features that may correspond to more complex shapes, and so on. And we also did a lot of theoretical work, and others have as well, to try to take the kinds of intuition I've talked about and turn them into actual math that helps us understand why these deep networks might generalize better. And so, for example, this work from 2014 at NeurIPS shows that a deep network that's using piecewise linear activation like ReLU has a number, decomposes the function it learns into piecewise linear pieces, and the number of pieces grows exponentially with the width of the network as well as with the depth of the network. Right. So that's nice. But if you look at the kinds of features that humans learn, they have something particular that I'm starting to, with years, I'm really focusing on this question of what are the kinds of high-level features that humans figure out, the kinds of features that we communicate with language, these abstract concepts and entities and abstract actions that allow us to describe the world and what is going on and so on. We don't yet have the recipe for this, and we would like to build learning systems that can disentangle the underlying explanations for what we are seeing. And that's driving a lot of modern research, but it's an idea that dates back to the early days of deep learning in the mid 2000s. One thing that is nice about the deep net and even a shallow net with a single hidden layer is that they're what we call universal approximators, which means that in principle, if we have enough units and enough parameters, we can train them well, then we can represent any reasonable function, like a continuous function or smooth enough functions. And of course, the deeper it is, as I said earlier, the more complex the functions we can represent, but potentially with less parameters. Now, how are we going to train these things? Because the universal approximation theorem tells us, in principle, there exists a set of weights for the network that allow it to represent a function we care about or close to a function we care about. But how do we get there? So we're going to have some data. And the recipe that has worked amazingly well for training these nets from the early days is based on what's called stochastic gradient descent. In other words, we see one example or a few examples, and we pretend this is the only thing we care about, and we do a small step to change the parameters towards getting a lower error on these examples. And then we get another batch of examples, and we do the same thing, and so on, and reiterate that. Now, to change the parameters in a direction that reduces the loss, we can use gradient-based methods. The gradient is the quantity that tells us the direction in the parameter space, where we would get for the smallest change in theta, the greatest bang for the buck, the greatest reduction in the loss. So that's the idea why we use gradient descent. The fact that we can update the parameters so often means that it's a bit noisy. That's why we call it stochastic gradient descent, but it also converges very quickly. We don't even need sometimes to go to the end of the data set if it's a very large data set, and sometimes we've already converged. So that's really one of the reasons why computationally neural nets have been so successful. Although there's a lot of recent research now trying to understand how SGD, stochastic gradient descent, also plays a role in the generalization ability of neural nets. It likes to find good solutions in the sense of better generalization, and that's also a pretty amazing property that we're only starting to understand. So as I said, the gradient is a derivative, the derivative of the loss, which is a scalar, like a number, with respect to the parameters. So that means the direction such that if we change theta by this quantity, but just a little bit, we would get the maximum change in the loss. So it's the best local descent direction. Let me change gears a little bit and cover a few topics quickly. So one of the things that I worked on, as I said, in the late 90s and early 2000s is learning representations for words in natural language models using neural nets. So the idea is that instead of representing the words just as a symbol, we're going to learn a representation for the word. So we're going to have a vector that's a free parameter for each word. We can think of that like a let's see if this works. Yeah. and we can plot them in 2D. It's an approximation, of course, they're in higher dimension. And what we find is that words that have nearby meaning will be close to each other in the representation. So for example, here you see all the European countries near each other. You see here a bunch of verbs being close to each other, and so on. So, and many more exciting properties were discovered after this work. For example, that you can do arithmetic on these word embeddings, and something meaningful would happen. Another idea I want to quickly mention is quite important for generalizing to new tasks, or being able to work with a problem where we don't have enough data for a particular task, but maybe we have other tasks that have enough data. We have a lot of these tasks. So then you get into the realm of multitask learning and meta learning and so on. And the general idea here that has to do again with the notion of representation is we're going to assume that all those tasks have something in common. Maybe they don't. In this case, it wouldn't help. But very often, you have a bunch of tasks that are related to each other. And so one thing you could do is say, have the early layers of a neural net, like in the figure, be shared across all the tasks. And then you have a separate path, which we call a head, for each task, that they have their own parameters, but just for transforming the shared representation into the predictions that are needed for each task. And that sort of architecture has been very successful. Sometimes people will have a main task they care about, let's say task A, but they want to improve the generalization on task A. So they use some other data of a related task, sometimes called an auxiliary task, to put to kind of put pressure on the representation to extract meaningful features that kind of work across many tasks. Another piece of work that has had a big impact in my career is the slightly more recent work on generative networks. In particular, the GANs, the generative adversarial networks, have been extremely popular. And they deviate from the usual pattern in neural nets where you have one objective function. You now have two networks, and they each have their own objective function, but they kind of work together, and you can show mathematically that together they optimize something like how to learn to generate data that looks like the training data. So we have a network that does the generative work, so it maps like a random Gaussian sample to an image. And then there's another network that's trained to classify whether that generated image really is it a real image or is it a generated image, right? And so it's like the game of people making counterfeit money, and then the people are trying to figure out if the counterfeit money is real or not. And they each kind of train based on the other, right? So the generator network is trained to try to defeat the discriminator network, and the discriminator network is trying to defeat the generator network by finding out what it is that is wrong, that is different from the real data. But of course, as the discriminator learns to figure out which features don't really work, don't fit the real data, that information is backpropagated into the generator network. So then it learns to fix those aspects of the images so that it will be indistinguishable. The image will be indistinguishable from the real images. And initially it didn't work that great, actually, because training these things is pretty tricky. But then people got better architectures and better ways of training them. And all of the images you're seeing here have been generated by some form of GANs. And you can see also the progression over the years. And nowadays we get these images that are so realistic, it's hard to know whether it's real or fake. We can also make those images conditional, meaning that we can put extra inputs to the generator, like a sentence, and it's going to generate an image depending on the sentence. So here on the right, bottom right, you would put a sentence like, this bird is red with white and has a very short beak, and it would generate image of a bird that is red with white and has a very short beak. It's pretty amazing. You can also transform images to images, like and in a way that's kind of creative. For example, transform a black and white image into a color image, and all kinds of things like this. But let me tell you about a project on the AI for social good camp that we've worked on using these GANs that we're very proud of and very excited about, soon to be on the website. It's the climate change visualization project. So, you know, and one issue with climate change is that even though there are a lot of people who recognize that, yeah, climate is changing because of humans, most people in many countries don't put a very high priority on this. You know, they think about survival and their job and the economy and so on. And so they don't realize that in the long run, it's going to be very damaging if we don't do anything about fossil fuels and greenhouse gases. So we were thinking, how could we better educate people so they have not just a scientific message about why it is important to act now, but also something that will touch them at an emotional level in the guts. And there's been a number of studies showing that if you show people images, it's somehow much more impactful to make them understand something and change their views on something than if you just give them text. There's the saying that an image is worth 1,000 words, but there's also an emotional aspect that images provide. And so we worked on a number of kind of how could we visualize the impact of climate change. So we worked on trying to generate fires, fog, but also floods. And floods are the most challenging. So what we wanted to do to personalize these images, to make them more impactful, is to create a website where people would enter their address, like on Street View, Google Street View, and then they could see the picture of their home flooded. So we take an image, like a normal image of a house or an apartment building, and we can apply this neural net that's been trained to transform the image into the same but flooded. So this is the project, and it's getting close to completion. It's been led by Sasha Lucioni, Dr. Schmidt, and many others, and we are very, very proud of that work. It's quite impressive what these systems are able to do. Now, let me go back to some of the advances in deep learning. Another really important advance, so besides the generative models, is the work on attention. Attention has changed really fundamentally what neural nets were about. The idea of attention is that we're gonna make a selection among a set of elements, and up to now we've been mostly using what's called soft attention, where we don't make a hard selection. We're going to give a weight between 0 and 1 to each element. For example, this was really developed in the context of machine translation. In machine translation, let's say I'm trying to translate the word économique in French, I guess no, the other way around. We're trying to translate the word economic in English into the economic as part of translating the whole sentence. Well, it turns out that in translation, often most of the information we need to find exactly the right word is localized in one place in the input. And so we want to kind of focus. We want the network to be able to, when it takes the next decision about the third word here, to, of course, get the gist of the whole sentence, but also focus on the specifics of maybe 1 or 2 words that matter for that translation. So this is where attention is useful. Like we don't embrace everything in the input. At some level of cognition, we focus on just a few elements the ones we have in mind, the ones we're able to talk about. So this is a tool that brains use, and we've incorporated that in neural nets. And in this work in 2014, we have a version of attention that is differentiable, meaning it's a soft attention. It's not a hard decision. I take this element. The fact that we have a soft attention makes it easier to learn where to attend. So this has been extremely successful, and you can use this to select the input of a neural net by using for each of these inputs a separate attention mechanism. And this has been really developed in what's called transformers. And transformers have become the state of the art. They use attention mechanisms over and over, and they have almost replaced neural nets, recurrent nets, which were dominant previously for handling sequences. So yeah, in many tasks in natural language, it makes sense to have this kind of focus. So if you're trying to come up with, the it in a sentence, like the animal didn't cross the street because it was too tired. In order to properly interpret that sentence, somehow you need to figure out what it refers to. And so at the next layer, there's going to be a representation of each word in a transformer, and we'd like the representation for it here to really extract information from one place, which is animal, because this is the word that it points to, and so it's to extract. This is still the idea of attention. One way to think about attention is a gating mechanism. So in the bottom on the right here, what you see, well, I guess in both figures, you have a set of elements. In the bottom you have 3, and then the top you have more, and the lower layer. And the upper layer needs to do some work, but it a piece of that work should be really focused on one of the items, but you don't know which one. So you take a weighted sum of all of the items, and you have another network, which is the attention mechanism, that outputs these weights. So we can have a softmax, for example. So these weights sum to 1, and they're positive. And at the end of learning, in the case of machine translation systems and now many transformers, those weights tend to be close to 1 hot, that it puts all the weight in one thing and it ignores the rest. But at the beginning, it doesn't know what is, where to put attention, and so it kind of distributes its attention all over the place, and then it learns to focus in the right places. All right, a concept that's related to attention is systematic generalization. So humans have this ability to generalize to new concepts. For example, in language, we do that all the time by recombining existing ones. And linguists have been studying that. But our current neural nets are not very good at that. And a lot of my current work is about this, like how do we design neural nets that can deal with things that are very much unlike what the model was trained on. Like you can read a science fiction scenario and understand it, even though it's completely out of this world, if I can say so. Or you can learn to drive in an unknown city, and you're going to be using attention to focus on just the things that matter, so you can generalize to this new setting, and combine the knowledge, the pieces of knowledge you have, in order to produce the right decisions in that new setting. So this is related to maybe a shift in learning theory as well. Like classical learning theory is based on the idea that all the examples come from the same distribution, including the test examples, but that doesn't really reflect the reality. We're going to have to use our network in a new setting. So how do we reuse our old knowledge such that we can generalize to the new setting? Well, this is where attention comes in. It allows us to focus on just the pieces of knowledge that are relevant, but that then requires, how do we learn a good factorization, a good modularization of knowledge? Yeah, I've been very much inspired in this line of work by the ideas of people like Daniel Kahneman, who introduced in psychology the notion of system 1 and system 2. So for example, when you're driving your car or your bike, to that matter, in a usual path that you are, you have a habit of taking that path, you don't need to think much consciously about what you're doing. It happens automatically. And it's hard to explain what is going on. It's happening at an unconscious level that is hard to verbalize. It calls upon implicit knowledge that you can't explain to others easily. And that's the kind of thing that current deep learning is good at. But really, we'd like to be able to do things that humans are able to do. This is what sometimes I call deep learning 2.0, and be able to manipulate knowledge that is more explicit, like in classical AI with symbolic symbols and rules and so on. But you can still learn. And when humans do that, they manipulate that knowledge sequentially. It's very slow, logical. You can reason, you can plan using these kinds of things, and you recombine pieces of knowledge you've seen before. So that's pretty much like the heart of my current research program. I'm going to skip some things and just go directly. I'll give you the slides later, so you can see the slides that I skipped. I want to finish this presentation by talking a little bit about responsible AI. People who design these algorithms, people who design the software that runs them, people who use AI systems to build new products, people who sell those products, governments who are involved in deciding, what should be, allowed and not allowed. All of these people have a responsibility because, well, machine learning used to be something we did in labs and universities, but now it's out there. It's in society, and it's having an impact on society. And so all of those people I named, they have a responsibility. We have a responsibility to see that the work we're doing is going to be used for good, to see that the social impact is positive, it's not abused. So why is it important? Because AI technology is powerful. AI is just a tool. I mean, there's nothing really magical here. It's just result of science and technology. We build tools. Humans have always been building tools. And normally we build tools because we need them to do something useful. But we can also, build weapons. We can build tools that could be dangerous, that could be misused, that could be used by one person to increase their wealth or their power at the expense of others. So that's why we have governments, right? To try to make sure that people act in a way that's good for society, that's good for most people, and not just good for them. So that begs the question in the case of AI, right? How do we regulate it? How do we incentivize companies and individuals so that they will use those tools in a way that's consistent with the norms and the values that we give ourselves in different countries? So we would like to encourage the use of AI for positive applications, for beneficial applications, like medical applications, the environment, education, justice, democracy, helping the people who are most in needs, like humanitarian applications. So we should put our efforts there. But this is not necessarily where companies want to go. Some of these things may not be profitable. And sometimes it's not just a matter of profit, it's power, right? I mean, powerful tools can be abused. Imagine if the Nazis or the Stalin era governments in Russia had access to AI, that they could monitor, surveil everyone, have cameras in the street, watch what everyone is doing, and use killer robots to kill their opponents. I mean, it would be really, really terrible. In addition, some of the issues with AI may just come because we're not thoughtful. For example, we have to think forward about, is the technology going to create a lot of misery for people who might lose their job? Or is it going to create problems in social media with the political bubbles and extremism that may arise when we just think about making more money with advertising? Or is it going to reinforce social biases and discrimination, or increase inequality and power concentration in a few people in companies and countries? So these are important questions that we need to think about and study. And one way to think about this, I call it the wisdom race, is that we need to make sure, as our tools become more powerful, that we become collectively wiser and individually wiser. Imagine that the tools we build become so powerful and so easy to access that like anybody would have in their hands the power of a nuclear bomb. So you can imagine that could be dangerous, right? So one thing we need to do is reduce, make sure that people everywhere around the planet are not angry, not frustrated with the rest of society. So they will not be as much, incentive to do things that are terrible and hurtful. So we need to make sure that every human is well-fed, well-educated, and healthy to avoid these problems, and of course manage the technology so that we avoid its misuse. And with these kinds of things in mind, in Montreal a few years ago, we decided to write a kind of declaration of principle for how AI should be used, and we laid down 10 principles. For each principle, there's like a whole discussion and sub-principles, but these are very broad things that apply to AI, but actually apply to any kind of tool we want to build, trying to maximize, of course, well-being, respect for autonomy, solidarity, democracy, equity, diversity and inclusion, prudence, responsibility, sustainability, and so on. So I will end my presentation here and be very glad to answer questions.
Thank you so much, Professor Yoshua. So if there is any question from the audience, just either you guys can raise your hands or send it in to the chat. Probably until then, I might have a couple of things to ask. It's really you are such an inspiration for most of us who got into machine learning and stuff like that. Since we got into physics and maths, we've been reading your papers and books and stuff like that. But recently it's a kind of obvious, or it's a trend for everyone in a millennial age or every researcher to get into machine learning, to dive into it, but it's not easy as it's expected, especially for some of us, from developing countries, right? So the first thing is everything is not accessible. The second thing is machine learning totally, it's computationally expensive, right? Yeah. So I mean, how do you see this? Like, what would be your insight about it? Because everyone is a researcher,
These are tough questions. Well, so first of all, there's a lot you can learn when you're on the path to mastering tools like in machine learning. There's a lot you can learn without having access to a lot of compute power. So of course you cannot reproduce many of the experiments that like Google and Facebook and Microsoft are doing, these huge neural nets. Even in my group in the university, we don't have the compute power for these kinds of things. It's just crazy, right?
I know.
So just forget it. There's a lot you can learn on a small scale. I mean, when I was doing my PhD, we had less compute power than you guys have in your laptop. So trust me, there's a lot you can learn without. I mean, of course, it would be better to have more compute power, and I wish governments and especially at the international community understand this and try to make it easier for democratizing the knowledge, to make it more accessible and easier for people around the world who don't have the means to develop that expertise, so they can develop the kinds of applications that they need in their country,
Right.
and do it by themselves. So that's my message for your question.
Okay, thank you so much. I can't see anything in the chat, or can't see any hands as well.
See, there's a question.
Okay, you got it.
How developing countries like Ethiopia should start in AI? All right. Well, the point number one is education. And I'm not familiar enough with how the education system is in Ethiopia, but it's really the base. Because in order to do something like machine learning, you need a good training in math, in computer science, and engineering. So if you don't invest in that kind of education, it's not going to work. And well, in addition, you want to, I understand developing countries don't have a lot of budget, but you can be, focusing in a few areas, not have to cover everything. And in areas where there's more of a chance of economic development and social positive impact, I think it's interesting for countries to invest. Yeah, reach out like you guys are doing to people in the rest of the world, and make coalitions with other countries in Africa. There's so much energy that I see right now around AI in Africa. It's very exciting. So keep at it. Okay, there's another one. Do you think GANs will be the future? I mean, I think GANs are now kind of an established thing, but we need to go beyond. So as I try to explain, the kind of monolithic architecture that are currently used in GANs and other generative models like VAEs and flow models are, I think, not exploiting some of the tricks, some of the inductive biases that human brains are exploiting in order to generalize and build an understanding of the world. So for example, with the current generative models, you're trained on a static data set. A lot of what I'm doing right now is to build generative models that can interact with the world. So with reinforcement learning, because when you interact with the world, you can have a chance to figure out some of the causal structure in the world. If I do something, what will be the consequence? And you don't get that in straight GANs. You need to embed them in like model-based reinforcement learning and other approaches where the learner is not just given a data set, it's given access to an environment and interacting with that environment. Okay.
That is another question, I think.
So we are developing a national AI policy. What is your advice on how to include responsibility of AI in professionals and startups? Nice. So this is a complex question. I would say the place in the world right now where they're most advanced in trying to turn things like the Montreal Declaration into government rules is Europe. So European Union. So the European Union has commissioned let's say a group of people, of experts, scholars, and public policy experts to try to set the rules of the game for companies that are using AI. And I think you don't need to reinvent the wheel, and you can draw from there. Now that's what I would answer to that question. Is it possible to get your time to comment the document? Which document? I don't know what.
I think they're talking about the national AI policy.
Well, I don't know. I mean, I'm not sure I have the time, but you can send it to me, and I can share it with other people who might be willing to give feedback. Absolutely, yeah, send it to me. Next question is: can we be effective if we invest on massive online open courses? Well, yeah, I think this is a great tool for democratizing knowledge. And now, designing new courses can be expensive, but it's I think it's a good investment. There's also something else that we're doing, that we've been doing at Mila, and there's a startup that was created to follow up on this, and that's the use of AI to create something like massive online open courses, but but interactive. So it's not just a bunch of videos and questions and answers, but it also has a kind of dialogue system, and it tracks the user to see, to try to know what is missing in their knowledge. So to provide the pieces of knowledge that are most relevant for that person, to personalize education, basically. So I'll be happy if somebody writes to me to give connections to that kind of work.
Sure. So if I'll have another one question, Dr. Dai. So where do you see deep learning like in the next, let's say, 10 years in terms of computational power, some amount of data needed, or something, to interpretability or something like that? Like, where do you see it?
I don't have a crystal ball, but in terms of computational power, I'm pretty sure that it's going to increase and the cost is going to decrease. There are so many companies building specialized chips for deep learning. So there was the earlier question, like, it's too expensive to do these experiments, but in reality, it's becoming cheaper. It's just that if you have less money, you're going to be like several years behind with respect to that. But as I said, you can do a lot of interesting research without having the top-notch supercomputers. And so yeah, I think the cost is going to go down. And where I see the field going, well, every researcher has their opinion on this, and I'm very excited by the challenge of building machines that can generalize better when they are outside of their comfort zone in a modified distribution. And I think that agency, so interactive learning is a key, as I mentioned. And that's why at Mila, we've made a sort of merge of deep learning and reinforcement learning. So I encourage people in this field to study not just deep learning, but also reinforcement learning. Of course, deep reinforcement learning, there's a lot of things going on there, which maybe not like next year, but on a 10-year horizon, I think are going to have a big impact on the advances in AI.
Okay, I think if I will have one more last question.
All right, go ahead.
Yeah. So I know Mila is, it's very successful in this area. Like I've been there and I know this thing. So that is one of the intention of the Prime Minister, Dr. Abiy Ahmed, had in his mind when he established this, the Artificial Intelligence Center to be, state-of-art research center in the continent, I would say in Africa, right? So what will be your suggestion? Because we've got, the deputy managers, the bosses here. So your suggestions, will really change that inside or, have something to them. So what will be your suggestion to be one of, good institution in the country, probably?
Right. So I think what the Canadian government did was very successful. So what they did is they concentrated their investment AI in three cities where there was already critical mass. And they before the Canadian strategy, most of the AI researchers that were trained in Canadian universities and did get their PhD in Canadian universities, they went to the US because the salaries were better and big companies with a lot of money and so on. And so I think, of course, the situation is very different in developing countries, but there's the same issue. You have a brain drain. So you need to create even one place, right, where it's really going to be attractive for people with expertise that could get a job in other countries, but they will want to stay in their country because they can fulfill their their passion and have the tools and the intellectual environment to do this kind of research and development. So that's one aspect. I mean, and another aspect, of course, is the governments have been stimulating the startup ecosystems, right? So helping people like students to start companies, to continue, for example, giving them their stipends while they start a company, so they can have a little bit of a buffer and create the seed of the company while before they get funding and so on. So both the focus in geography and in areas allows to provide good conditions for researchers who want to do something for their country and can have an alternative to going to work in the richer countries. I think that's a good strategy.
Thank you so much. Okay, one more question. I think you can read it.
Yeah, I think I answered already. Yeah, of course, the technologists and engineers have a duty to think about the societal impact of AI, such as labor displacement. Of course, yes, that was part of my message.
Okay. Yeah, so thank you so much, Yoshua Bengio, for your time, to share your thoughts about AI and insights about the national level, AI thing.
Sorry.
Yeah.
Sorry. That's right. Before you are closing, I have dropped one question.
Okay.
Yes.
Actually, it is 3 questions. I need a professor to address those questions.
Oh, can we create a collaboration in capacity building, joint research, student exchange? Yeah, I mean, this is something that we are trying to do. Of course, I mean, Mila does, as Israel can witness, has a very small group of exchange students from various parts in the world. So we don't have a huge capacity for this, but we have been doing it, and we're excited to continue that kind of thing. Oh, how can we attend courses from Mila? Well, I mean, courses that are physical, it's hard to attend, but a lot of the activities we have now are virtual. So it might be possible to attend or at least to get to attend some of these virtual meetings. So yeah, that's, I think, something we're going to have more and more around the world. By the way, it's happening because of the pandemic. Everything is more and more virtual. Every lecture is, many lectures are being recorded. So, both from Mila and many other places around the world, you can find so many conferences and lectures. Everything is online. It's amazing. And so you should really take advantage of that.
Yeah.
All right.
So thank you so much. I think as a suggestion, probably I could say something for the collaboration. I remember visualizing the impact of climate change using GAN was open to upload data and stuff like that. Probably like people can upload different images. That's how you start collaborations probably. Yeah. So thank you so much, Professor Yoshua, for your time.
My pleasure.
To share your thoughts and insights about artificial intelligence. We would love to have you, another time as well to give to give us more things. Yeah, thank you so much.
You're welcome. Have a good end of day. Bye, everyone.
Bye, Professor.
Bye, Professor.
Thank you.